Birimlerden çeyrek başlayalım.
EMF, okay. What should be the unit of EMF? Whose unit is? Okay, E dot dl. So, what's the unit? What's the unit of E? Times the length. Well, you see, E, let's write it SC squared, there's no square, divided by length, meter. What's the unit of SC? Well, you see, in fact, we don't need that. You see, if the units match, unit of the electric field times the unit of L should be equal to unit of B0 times the unit of A over C, unit of omega. Sine omega t is unitless. Okay. Now, what is the unit of B0? Now, B0 and E have the same unit. So, unit of length should be equal to unit of area divided by unit of C times unit of omega. Well, C, unit of A, C has the unit of length times unit of omega. Unit of omega. So which has the unit of length. So everything matches. Let's get the solenoid example. So let's assume we have a solenoid. And around it we put another ring. There's a current I running through it. Or if you look at it from the top view, what is the direction of the B field inside the solenoid? The B field is downward. And let's assume that B field has this form B0 sine omega t. So we are kind of adjusting the current such that the B will be B0 sine omega t. Now let's say, assume we are looking from the top. So this is our solenoid, let's say it has a radius r, the B field is inside. Let's say the outer ring has a radius d. Let's choose a direction to it. Should we choose the direction of the outer ring, clockwise or counterclockwise? Clockwise. What's the direction of ds? Inside the screen. Well, you see, B0 is positive if I is positive. I is running in that sense. I0 is positive, let's say, at t equal to 0. Now, what is the flux passing through my outer loop? B0 sine omega t, but remember, here in this region, B is always 0. B is non-zero only in this region. So the flux in the integral, we can divide the area into two parts. One part where there is a magnetic B field, one part there is not a B field. The only contribution to the B flux will be from the region which has a magnetic field, so it will be just pi r squared. This is our phi B. So epsilon is equal to minus 1 over c d phi b by dt. This will be equal to minus b0 pi r squared omega over c times cosine omega t. This is our induced EMF. Yes. Now, what is the electric field? Well, EMF will be twice this one. Why twice? Because my wire goes around twice in that choice. Well, let's say, what is the electric field? You see, if we would go around once, the EMF will be 2 pi times d times E, if you would go around once. In this case, the EMF is minus 2 b0 pi r squared over c times cosine omega t. No, there's no 2. Pi is cancelled. So there will be an electric field which will be given by minus b0 r squared over 2c cosine omega t over d. It will be going around my solenoid.
Is there omega?
Yes, omega. You see that around the solenoid there is an electric field outside. Now this is kind of weird. You see, outside the B field is 0. But nevertheless, we get an electric field if the B field inside the solenoid is changing. Now let's look at inside the solenoid. Solenoid. That is, D is less than R. Now basically the derivation will be more or less equal. So 2 pi D times E, this should be equal to minus B0 pi omega over C cosine omega t. Now this time we will actually use the D squared, because inside the solenoid all of my loop is within a B field. So that's why the area of my loop is pi d squared. I use all the area. In the first case, some part of the area of my loop wasn't in a B field, so I only took the part that is in a B field, and that was constant. The area that was subject to a B field was constant if I am outside the solenoid. So this tells me that the E field inside the solenoid is just, again, B is cancelled. These, one of them will cancel. B0 omega over 2c times d times cosine omega t. So basically the intensity of the E field is a function of the distance. Let's say this is R. Initially it increases linearly, and then it decays as 1 over d. This is at a given time. Now let's try to understand what is creating this electric field, E field. We said that, okay, it's the changing B field that is creating the E field, but so outside the solenoid there is no B field, but nevertheless we still get an electric field. So how is that generated? Now to understand what's going on, let's look at this problem again. So we had this rod moving in a uniform B field case. Okay, this is in one reference frame where the B was uniform. We can go to another reference frame where the rod is at rest. In that reference frame, it's the B fields that are moving around, the B field lines that are moving. So what creates this, the electric field, is actually the motion of the B field lines. So if the B field lines are moving, they create an electric field. And the direction of the electric field that they create will be given by V cross B. Plus or minus. Plus. How do you know? Well, let's say in this reference frame in which the B field lines are at rest, the current will be pushed upward in the rod. So in the other reference frame in which the current is at rest, the electric field should be pointing upward in the other reference frame. V is towards the left, so V cross B is downward. So E field should be minus. Remember, in this expression, V is not the velocity of the rod. V is the velocity of the B field lines. So if you know the direction of the B field, of the velocity of the B field lines, if you know B, you can determine the direction of the electric field at that point. Now let's apply this principle to a few problems. A wire, a straight wire. So there's a current I, let's say, this is the other perspective. What is the direction of the B field lines at a given instant? Counterclockwise. These are our B field lines, well, one of them. Suppose you increase the current, what happens? This intensity will increase, but how will that happen? You see, if you increase I, we know that B should increase. Well, B is proportional to the density of the B field lines. So the density of the B field lines should increase. That is, their number should also increase. Which basically means that as you are increasing the current, new B field lines will be created just close to the wire, and they will start spreading out. They will be pushing the other B field lines, compressing them also at the same time. The number increases, and they will also push them out, the new B field lines. So you have additional B field lines created, and they will be moving outward. So what's the direction of the electric field now? It will be in the direction of, you see, minus V cross B, or B cross in the direction of B cross V. Let's say at this point, B is upward, V is towards the left. So the induced electric field will be downward. It will be into the screen. in fact, everywhere the induced E field will be into the screen for the same reason. So that is, if we have this infinite wire, and if I is increasing, so there will be induced electric fields in the opposite direction. Well, let's see if this makes sense. We already know if we put a loop over here, we had already determined the direction of the induced current running through the loop. What was the direction of the induced current running through the loop? If I is increasing, I is increasing, B is increasing into the screen. So the current should be such that B, it should create an additional B out of the screen. So that is, it should be in the counterclockwise sense. Well, let's see, there is an electric field pushing the current in the counterclockwise sense on the left side. There is an electric field pushing the current in the clockwise sense on the right side of my loop. But the induced electric field on the left side will be stronger. So the net effect will be a current running in the counterclockwise sense. So at least things are kind of consistent with each other. Now let's also look at the case when di by dt is less than 0. We have I, the current is decreasing. So here we have a one B field line. So what happens to the B field lines as the current is decreasing? Their number should decrease. Their density should decrease, but how does it happen? Do they just contract? Well, they don't contract. Because you see, the problem is, you see, this is where the current is, let's say. There is a B field line, I don't know, in octocant. As the current here is changing, the B field line at that distance has no idea that the current is changing yet. So how will it know that it should contract? It does not. What actually happens is, as you are decreasing the current I, you are creating additional B field lines, but in the opposite direction. So you will be creating some B field lines in the opposite sense. Well, you see, the B field lines actually do not even exist. It's our mathematical invention, but kind of we have to be consistent on our description. It gives us some kind of an intuitive description. Now, the problem is, as you change the current, something should go outside and tell the other B field lines that they should disappear, some of them. So without this messenger, they cannot just contract. This is our messenger. So this additional B field in the opposite direction, it starts spreading, and it cancels some of the B field lines, so that their number decreases, and hence their density decreases. And this will be spreading out. So let's see, what is the direction of the electric field at that point? The induced electric field is always B cross V. So V is in this somewhat upward, B is in towards the left, towards the right, V cross B into the screen. No. Am I right? Yes. Hold on, did we do a mistake over here? Yeah, here we did a mistake. No? No, B cross V, yes. It's B cross V. So B is towards the right, B cross V is out of the screen. Yes. This is the direction of the induced electric field in this case. So in this case, we have the induced current running upward in the direction of the current. Now, this is just another way of determining the direction of the B field, of the induced E field, sorry. But nevertheless, you should know that you should know the direction of the velocity of the B field lines in order to determine what should be the direction of the E field lines. Now let's go back to our example of the solenoid. So that's basically what we are trying to understand. Now this time let's assume we have a finite solenoid, not an infinite one. Oops, sorry. Let's first look what's happening inside the solenoid. If this is the direction of I, the B field created is outward. It's uniform. If I is increasing, then the number of B field lines inside my solenoid should increase. Well, everything is quite symmetrical, so they should be kind of being compressed in a symmetrical manner. So all of them will just move towards the center. And we will have more B field lines generated. So they will just go towards the center. Now let's see, the direction of induced E field is B cross V. Well, let's see, at this point, B is towards you, V is into the, towards the center, B cross V downward. Right, so this is the direction of the induced electric field. So induced electric field lines basically form loops in our solenoid. They are not uniform. Well, this also makes sense. Just imagine you put a wire there. The induced current should be in the direction as to reduce the effect that it creates. The effect that is creating the induced current will be the increase of B out of the screen, so the current should create an additional B field into the screen. And that is only possible if the current is running clockwise sense. Now let's consider the outside region. So this is basically how we can determine the direction of the induced electric field and what's going on inside the solenoid. Let's look at outside the solenoid. The finite case, finite solenoid case. This is the direction of the current, or this is the direction of the current. So B field lines, they will basically form, they should form closed loops. They will have such a shape. These are our B field lines. You see that the B field outside the solenoid is small. Just look at the densities. They are quite dense inside the solenoid. Outside, they are not so dense. So if you make the solenoid longer and longer, the density outside will be less and less. That's why in the ideal solenoid example, the B field outside is exactly 0. Because it just goes to some number over the length of the solenoid, which as the length goes to infinity, the B field goes to 0 outside. Now let's assume we are increasing the current. So we are creating additional B field lines. But remember, B field lines should always form loops. So if you create an additional one, it should also form loops. You see, you create an additional one over here. There is a B field line both inside and also outside. Even if the solenoid is infinite, the B field line should form closed loops. They should form loops that close at infinity, let's say. But they will start very close to the wire itself. So basically what's happening if we have an ideal solenoid is outside the B field is 0. But as you are increasing the current I, you are creating additional B field lines both inside and outside. But the B field lines, the additional B field lines outside, they just go move to infinity. But they have a velocity. And if you imagine a wire, they are crossing this wire. So that is why you get a E field outside, even though the B field was 0. Okay, so you are creating these closed loops. In the case of the solenoid, the loops, okay, the B field lines goes along the solenoid. The edges of the solenoid, let's say you have a very large solenoid, not necessarily infinite, a very large one. So these B field lines, they should leave the edge and then turn around and go to the other edge of the solenoid. Okay? Well, since this distance between the edges is, they will start very close to the wire, these loops. So you have this solenoid. Initially, the B field line is created very close to the wire. But the outer B field line, they should go to infinity. It just spreads out. And at a given time, when you look at the outside, the density of the B field lines outside is negligible. But you have this motion of the B field line nevertheless. And it is this motion which creates the electric field. It is not the density of the B field lines, it is the motion of the B field lines that is creating the electric field. So although the density is negligible outside our solenoid, nevertheless the motion is not negligible. And it creates this electric field. Well, this is a crude approximation, a crude picture. The speed will be the speed of light. Yeah, you see there are many idealizations in the case of an infinite solenoid. In like, if you want to increase the energy of an infinite solenoid is infinite. To increase it, you need infinite energy, which kind of doesn't make sense. But the speed of these B field lines, their spreading speed, let's say in this case, should be the speed of light. Any other questions? Okay. No questions?
The spreading of B field lines is because of increasing I.
I mean, you see, you have I is increasing. So you need, No, you need additional B field lines. And they will spread. I mean, once you create the B field lines, they will spread. And the change in I is what is creating this additional B field lines.
You said E is equal to minus B cross B, right?
Mm-hmm.
The unit on that next.
It's the direction. Let's say the direction of, well, in fact, the magnitude also. For example, for a moving charge, we said that B is equal to V cross E, right? V over C cross E. Let's calculate V cross E induced. This is equal to V cross V over C, which is B times V squared over C minus V times B dot V. Assume, which will turn out to be correct, B is orthogonal to B. B dot V over C. Which basically tells me that B dot V is equal to 0. And V is equal to C. So B is equal to V over C cross E induced. Yeah, we will make these derivations more rigorous. It doesn't really make sense for a B field moving along itself. So if you have this uniform B field, what does it mean that the B field line is moving along itself? It doesn't change. So in that sense, B has to be always perpendicular to V. V being the speed of the magnetic field lines, perpendicular to its direction. And V is equal to C. It's just what I said, that the B field lines, once they are creating, they will be spreading at the speed of light C. But just, these are kind of hand-wavy arguments. I mean, you see, inside the solenoid, they are not moving at the speed of light. Their change basically depends on how you are increasing I. Because I determine the total number inside. Outside, there is nothing that confines the B field lines. So they just spread freely. In that case, they have the speed C. Of course, if you go towards the edges of the solenoid, well, it cannot be C. They're not moving at that speed. So when you're talking about the speed of the B field lines, you should be a bit careful about what you mean. But in this derivation, I have been also quite sketchy, because you see this V over here was actually V0, not the speed of the B field lines. That V was the speed of the point charge, the velocity of the point charge. So there seems to be something over there, but just don't take these, just keep these equalities, these ones, not as a quantitative equality, and this description of the moving B field lines as a quantitative description, but rather a qualitative description. So how do you determine the direction of the E field line, B field line, or the E field line? At least in simple systems, there are some easy ways you can determine what is the direction of the motion of the B field lines, and once you determine the direction of the motion of the B field lines, from that point you can determine the direction of the induced field. If you can avoid this description, it is even better, because it's not strictly quantitatively correct description. It's just to give you a qualitative picture of what is going on. So if you want to find the real direction of the E field, the real magnitude of the E field, this is what you should use. That is one of the equations that you should use. This gives you the quantitative picture. The other ones are just qualitative, to make visualization some kind of easier. Don't take them at their face values. So basically the question is, what do you mean by the motion of the B field lines? How do you measure the B field lines? You actually cannot measure B field lines anyway. So what does it make sense to talk about the motion of the B field lines? Now, from a physical perspective, not really. What does make sense is you can talk about the changes in the B field lines. So you make a change close to a wire. How does that change move? We will see that that change moves exactly at the speed of light, independent of what is creating that change. Okay, any last minute questions? Okay, so see you on Wednesday.